Welcome back to the second part of section 21.2. We're talking about unsaturated hydrocarbons, those with any amount of double or triple bonds. And today we're going to finish up the chapter section and talk about aromatic hydrocarbons. Now, when we see this word aromatic, we're not talking about necessarily aromas. However, that's where this word came from. Some of the earliest aromatic hydrocarbons were found to have distinct aromas, distinct smells. That does not mean aromatic hydrocarbons always have a distinct aroma, but this is where we get that original name from. So it's a special class, and the simplest of this class is benzene. So that's not a systematic name necessarily, but that is the official name for this compound, benzene. And it's a ring of six carbon atoms tied together. So we see alternating single and double bonds in these aromatic type structures. And for we to call it aromatic hydrocarbon, it has to have at least one benzene ring in the structure, and it can have multiple rings as well. So let's take a look at this. Here's the different ways we can draw benzene. And if we take a look here, we see we have 1, 2, 3, 4, 5, 6 carbons there. And off of each carbon, we have a single H, and it's an alternating single bond, double bond between each one of them. That alternating is key. That gives this something called aromaticity, where we have the ability for these electrons to move from these pi orbitals into this empty spot. And then that pushes these over here, and that pushes these over here. So they can move all around. That's why we can draw this like this, or we can draw it like this. Notice where the double bond and single bonds are. And this is the skeletal structure that we use a lot in organic chemistry as well. So each one of these points here, there's a carbon and an assumed extra bond. We're not saying that there's only 3 things bonded to this carbon here. You have to fill it up with hydrogens. So it's assumed that there's this other H here in these skeletal structures. So again, this bond picture here is not static. At any point in time, this could move here, this could move here, and this could move here, which would give us this structure. So in reality, this is just a static page drawing, but we don't know where those electrons really are. This is probably a better way to draw it over here, where you actually have this circle indicating that there's a ring of electron density all throughout this system. So this is benzene, the most simplest form of the aromatic hydrocarbons. And what's cool about this is because of this resonance structure, let's look at this double bond, let's say this is CH3 and this is CH3, versus the double bonds we find in benzene. These have the ability to move around. They're delocalized. These are localized. If this tried to move to here, let's draw that structure out actually. What would happen? Well, it would be CH3. And remember, there's only one H coming off of here. So what's happening here? Now that has a positive charge, and this has a negative charge. That is a really high energy situation. That's not going to want to do that. However, if you have alternating next to each other, they're equivalent bonds as they move, and they're not going to produce any formal charges of positive or negative. So what that means is delocalized electrons are less reactive. It's not like this dense section of electrons that it wants to go out and do reactions. They are moving around. They're less reactive than localized electrons. So aromatic compounds we find are more stable than expected versus normal isolated double bonds. So if I'm actually going to look to the next here slide, shows this ball and stick method, and I wanted to use the room on this slide to show the pi system that's going on here. So I'm going to turn this over and from a different perspective, kind of draw it looking at it kind of from like this side. Actually, I can do better with my lines here, to be honest. So let's say this is 1, 2, 3, 1, 2, 3, etc. That's where I'm looking at here. So at each carbon, remember in the middle, there's a sigma overlap in the middle. That's the one bond between these, between 1 and 2. The second bond comes from the p orbital. So the p sigma overlap. So there's a double bond. And this one is a single bond. So that's just a overlap there. This is 2 going to 3, 2 to 3. But then there's a double bond from this carbon to this carbon. So at each one of these points, we have these pi orbitals. And that means these electrons in the pi orbitals can kind of move around between the pi orbitals. That's where we get this delocalization from. So they have this delocalized pi system, which gives this a very good, gives it a very stable structure. Also, it makes sure we know that this is a flat molecule again. These are all sp2 centers, and you cannot turn this bond, otherwise you'd break the pi bond. So it's a flat system like this. This is looking at it from kind of the side. So what reactions are we going to talk about? Well, they do react with things, but they're not going to add across the double bond here. Remember, usually if we see a double bond, let's say this is ethene and reacted with Br2. We add Brs to both of those carbons. Br, H, H, Br, H, H. An addition reaction across the double bond. And we don't really find that happening in these aromatic compounds. So instead what we see are substitution reactions, kind of like an alkane chain, where we're going to substitute one of these H's with a bromine here. And we're also using a catalyst, another additional reaction here, or compound here, to do this as well. So metal centers become pretty important in organic chemistry as well. So we're going to replace this one, and that's just arbitrary, right? It's a symmetrical molecule. We could replace any of these, but to make it simple, they just put it right there. And we're going to get HBr as our other product in this reaction. So there's a simple reaction. This could be I2, Cl2, etc. would react the same way using the appropriate catalyst as well. And oh, just to point out, how are you going to write these condensed? Well, C6H6 plus Br2, and then you just replace one of the H's with a Br. So H5Br, and this goes over here. Now, how do we actually name these substituted benzene derivatives? Well, we're going to use benzene as our parent name for all of these. So if it's mono-substituted, like these, there's just one substituent on these. You simply name them like we were before. The CH3 group becomes a methyl group. So this is methylbenzene. And again, this could have been drawn like this, the CH group here or here, for example, but it's arbitrary where you put this. It's just at one spot. So we don't need to say one methylbenzene. It's just methylbenzene. Same thing for these halogens, bromobenzene. So if you had, for example, CH2CH3, that is an ethyl group. Propyl, butyl, pentyl, etc. You can have these big side groups coming off. So that would just be ethylbenzene. Okay, so now what if we have a situation where there are more than one of the same type of group, for example? So you've got multiple things on there, and they could be at different positions. So we use these, you'll see these prefixes come out a lot, ortho, meta, and para. These are specific positions relative to the one position on your ring. So let's just look at, I'll explain these rules on this page first. So if we look at this first compound, we have a bromine here and a bromine here. So we need to name one of these the one position. So let's just say we pick this as our one position. Okay, so that's our one position. This spot relative to that bromine one position is called the ortho position. Or the name might just say 1, 2 as the positions. So you'll see these named both ways. So how would we name this? Just like before, if we have multiple substituents on a straight chain or something, we need to tell you where they are. And then if there's two of them, we use the di. So we've got one at the one position, the two position, and dibromobenzene. Or we could call this ortho dibromobenzene. That tells us there's an additional bromine at the ortho position. So let's look at the next one. If this is our 1 right here, relative to that, you go 1, 2, 3. That position right there, we call that the meta position. So we've got ortho, meta, and down here we call para on this side. So again, two ways we can name this. 1, 2, 3 dibromobenzene. So 1, 3 dibromo. Or we can just call it meta dibromo. As in, we know we have one here, so there's also one at the meta position. So meta, or you might see them O, M, and P as even more abbreviated versions of that. Finally, in this case, we have 1, 2, 3, 4 away. That's the para position. So again, we can call this 1, 4 dibromobenzene, para or P dibromobenzene. So that's how we name these type of di-substituted, multiple substituted benzene rings. And we're going to go to the next slide to look at this rule. When different types of groups are present, the groups are numbered in order of their alphabet, the order of alphabetically. So let's go ahead and look at those. So in this case, we have an iodo group and a bromo group on here. In this case, we have a methyl group and a chloro group. So same thing. How do we number this? Well, right away, you could just start numbering this 1, 2, 3. But no, you got to think, what's the proper alphabetical numbering for this? We instead are going to start numbering with the one that comes first in the alphabet. So B, bromo. So that gets the 1 position, and this gets the 2, and this gets the 3. So we're going to call this 1 bromo dash 3 iodo benzene. For this one over here, same process. We have to start numbering them somewhere. So we think what comes before in the alphabet? The C before the M in methyl. So this is the 1 position, and this becomes the 4 position, not the opposite. We don't want to number this 1, 4. So this is just 1 chloro dash 4 methyl benzene. Okay, let's do a little bit of practice here. So this just says draw chlorobenzene. Pretty simple example here. I'm going to bring up my, give me 1 second. Always doing this live, right? Okay. So for chlorobenzene, you just have to think, okay, got to remember what benzene means. That means we're talking this structure, and it becomes a lot easier just to draw the skeletal structure. Notice where I put the double bonds? That was arbitrary. I could have drawn it like this and put a double bond there, for example. Doesn't matter. They're equivalent structures. So get rid of that one. Chloro just means Cl. And again, it doesn't matter where I draw it. Usually we're just going to draw it right there. But it's just as correct to draw it anywhere else. It's the same structure. If I just physically turn the structure around, just turn it this direction, I can end up with this structure. I'm physically turning the molecule. So it's the same molecule, just physically turned around its base. So that would be chlorobenzene. I could also ask the question, draw the structure of ethyl benzene. Same thing. Now, what is an ethyl group? So again, an ethyl group is going to be coming off of a carbon chain, whatever this chain is. And a lot of times you'll also see generic things like this is just something, and you'll put a squiggly line. That's not a great one. That means it's connected to something over here. But what does the ethyl group look like? It's CH2, CH3. Make sure that's a CH2, CH3, or you could draw it out to make sure you remember how many carbons and hydrogens there are. So there we go. So I just need to do this and then CH2, CH3. Again, I could have put it here, here, wherever you want. So those are simple structures there. What about this way works great. This way works great. Notice they use the circle. I didn't put a circle in there, and that's okay. You can also draw it like this. There's nothing wrong with drawing the double bonds and not drawing the circle method, or you could have drawn them and they're more full pictures. Either way works great for these type of drawings, unless it specifically asks you to draw it a certain way. Okay, let's practice some naming. So go ahead and pause the video here to give yourself a second to try to name these on your own. And we're back. So let's tackle this first one here. Okay, so now we have two different types of derivatives on here. So I need to make sure I number these properly. Alphabetical numbering. So F versus C. Sorry, not C. This is a methyl group. It's a fluoro group. So, actually, U becomes a 4O, which is something I always forget. This is FLUORO, fluoro group. So the F becomes numbered first. F comes before M, so we're going to number this 1, 2, 3. And again, not 1, 2, 3, 4, 5. We want to minimize the numbers. So 1, 2, 3. Also, this is orthometa. This is the meta position. So we could also call it meta. But if there's two substituents on here that are different, we typically just use the numbers. So just use numbers. So what will we name this? 1 fluoro dash 3 dash methyl benzene. There we go. Okay, over here, again, we're going to stick with numbers and not orthometapara. In this case, well, it's pretty simple because it doesn't matter if I do 1, 2. It's the same as if I did the other side 1, 2. I could do 1, 2, whatever. It's a 1, 2. So, and it's a diiodo. So 1, 2 di, and don't forget the figure I for iodo. It looks kind of weird. Whoops. Diiodo. Weird looking set of letters. Benzene. Ooh. Notice there's no spaces either. Just methylbenzene and diodobenzene, just one word. And there are two practice for that. Go into your book. There's a lot more practice and the practice problems that I assigned to get these down. So, double checking our answers. Yep, 1 fluoro, 3 methyl, 1, 2 diodobenzene. There we go. Okay, so let's do a little bit of review here. Unsaturated. That means we have some amount of double or triple bonds. If you have any number, 1, 2, 3, doesn't matter, it's an unsaturated compound. Alkenes have one or more of these double bonds. Alkynes have one or more triple bond. And then aromatic hydrocarbons are the special ring versions of these with alternating single and double bonds. Alkenes and alkynes are much more reactive than alkanes. Those double bonds do a lot more chemistry. These spaces of electron density can go out and do reactions. And we looked at some reactions with halogens and hydrogen halides, so HBr, HCl, things like that, at room temperature addition reactions. Aromatic hydrocarbons go under substitution reactions, but not additions like the alkenes. And we name these very similar to alkanes, except that we give the double or triple bond is given the lowest possible number. It takes priority on the numbering. So you want to name those at the lowest possible number. And then we talked about how we name benzene derivatives. using the orthometapara sometimes. That's the older version, but usually we're using the numbering system. The first group is assigned to 1, depending alphabetically. And there we go. There is our short ending to section 21.2. I will see you guys next time for section 21.3.